Hi, welcome to this presentation series on cryptography problems. Today I'm going to talk about a really fascinating problem related to key exchange. So this was an interesting homework problem given to grad students. I will talk about something called Merkle's Puzzles, beautiful idea, how to establish a common key over an insecure channel. So I'll introduce you the notion of Merkle puzzle and then talk about the complexity. Okay, so let's take the problem statement here. It's basically the same problem that was given to the students. I rewrote it and deleted some parts that are not relevant. Okay, our friends Alice and Bob want to agree on a shared symmetric key over an insecure channel. The channel is just, you can imagine an abstraction for exchanging messages. And they wanted to use Merkle puzzles for establishing this common symmetric key. I will talk about the Merkle puzzle first, and then I will show you what is the complexity for Alice and Bob to agree on a common key, and what about the computational complexity for Eve, the evil Eve who's trying to break the channel, of course. Okay, so let's get started straight into the Merkle puzzle core idea. Okay, Merkle puzzle was published back in 1974. Actually, it was submitted to proposal or submitted for publication back in 1974. It has an interesting story. I will come back to the story at the end, but at this point, I will focus on the technical aspect first. The idea of the puzzle is really out-of-box thinking, in my opinion. So remember, Alex and Bob wants to talk to each other, but the channel itself is insecure, so they can't simply exchange a key over an insecure channel. The idea of the Merkle puzzle is that, let's say you have participants X and Y. You could imagine Alice and Bob, although the author in this paper never uses Alice and Bob for some reason. I don't know why, but anyway. X is the Alice and Y is Bob. You can imagine like that. The idea is that Alice will generate so-called puzzles, bunch of puzzles, and send it to Bob. Bob will solve one of the puzzles and give indication back to Alice which puzzle Bob solved. From there, Alice knows exactly the key Bob has. That's the very, very high level idea. A lot of details I will explain quickly. So the idea is simple at this point. The idea is that Bob has to solve one puzzle out of millions of puzzles sent by Alice. And then he will give feedback to Alice saying, I solved puzzle number 10, for example. Not exactly puzzle number, but the content within the puzzle itself, he will tell. From there, they both agree on the same key. Okay, let's walk through the idea step by step. First step is Alice generates lots of puzzles. What does it really mean by generating a lot of puzzles? Alice picks up two random numbers. Let me zoom into the algorithm. Okay, here is the algorithm part, right? Alice generates two random numbers, K1 and K2, large random numbers. And then Alice also generates a constant, which is again a large random number. She sends the constant in clear text to the receiver, in this case Bob. So Bob would get a constant, okay, a large number, random number. Even Eve can see that constant, not a problem. Okay, let's walk through the for loop now. The for loop runs from 1 to n. N is the number of puzzles. F is the symmetric function, like AES. At that time, there was no AES. You can imagine like DES at the time, right? F is a symmetric function, encryption function. It takes the key as the first argument, and then the data as the second argument. In this case, K1 is the key, random number. Alice encrypts number 1 using key K1, right, to get an ID, which is a random number again, if we assume F is a pseudo-random function. And then she generates something called key based on the ID, okay? So ID is another argument, right, here, second argument, and uses the second key to generate a key. So what she has generated so far is an ID and a key pair, right? All right, then the third thing she does is she generates another random number called random key. Okay, what is C here? C is some kind of a constant. It's a constant, in fact. I will explain what the constant really means in this case in a moment. But once she has the ID and the key, she encrypts that ID and the key together with the constant, which she sent it in clear text to Bob. And now she transmits this puzzle. Okay, so what is Eve seeing it? Eve is actually seeing only the constant, of course, in clear text. She doesn't, Eve doesn't know ID or key because it's packaged within the ciphertext that was sent, right? The puzzle itself is output of encrypting ID and key and constant together. You can imagine ID, key, and constant are appended together, or concatenated to form one string, and then apply a DES or something like that at the time, right? And then we transmit the puzzle to the other end. Okay. So how many puzzles Alice is generating? She's generating n puzzles. N could be million or billion, whatever. That's something configurable. And C is another constant, right? Why do we need the C? C can be 1. In that case, what she's actually generating is basically, if n is say 2 power 32, she would be generating 2 power 32 puzzles. Each puzzle itself is encrypted by a key, which can be one of the 2 power 32 numbers, right? Because the key size is basically a random number, C times n. Okay. What would Bob do with that puzzle? Bob will randomly pick one of the puzzles. Let's go to Bob's side. Okay. What does Bob do? This part of the for loop is not that important. I will skip that a little bit. What Bob does is he randomly selects one of the puzzles to solve. That's the random part. Remember the constant that Alice sent to Bob is his clear text constant. So everybody can see it. Of course, Bob can also see that. What Bob is going to do is now actually, he gets into a loop, right? Remember the key strength was C times n. So he does brute forcing. Usually good guys don't do brute forcing, but in this case, Bob, being a good guy, is going to brute force for all possible keys in such a way that after he decrypts, here is the F inverse, right? He inverts the function F by guessing each key. The key number is 1 to C times n. The puzzle is the puzzle that he currently picked, right? From the collection of puzzles, he picked one of the puzzles. If after decrypting, he gets the temporary constant the same as the constant Alice sent, then he knows that he found the right key. Okay. Otherwise, he wouldn't have gotten the same constant Alice sent as part of the payload. In fact, as part of the clear text as well. Otherwise, he doesn't know what to compare against. Okay. So once he found a match, he knows he found the right key for that particular puzzle. Okay. And now he will send back the ID. How does he know the ID? ID, remember, is part of the puzzle itself, right? The puzzle sent by Alice has ID, a key, and a constant. All of them put together, encrypted using the random key. Bob was just brute forcing the random key. As soon as he found this exact constant in that ciphertext, he knows that that particular key is the key that was used to encrypt this particular puzzle. Okay, so therefore he gets the ID and he sends back the ID to Alice, saying that this is the ID I wanted to use. Okay, that's also coming in clear text. Okay, Eve can see that. But what will Alice do with that? Once she receives the ID, she applies the same function F with K2, ID. Why do we do that? Why is Alice doing that? Well, let's look at this part. One moment. See here, the key we need is computed through F, which is a symmetric function. K2, of course, Alice already knows that. ID is the data that was sent now by Bob to Alice, saying that I decided to use this ID. Okay, now both Alice and Bob have the same key. So this is basically it. The idea is extremely simple. If I can quickly sketch this in plain English, I will just write it in pseudocode for a moment. So the idea is this, that first we just call it idea.txt as informal algorithm steps, right? Alice sends n puzzles, right? What is in each puzzle? Each puzzle has basically puzzle 1, let's call it puzzle 1 for a moment. Puzzle 1 has something like this: an ID, a key, and a constant, right? This is encrypted, of course. So we encrypt this using a random key, right? And she sends that to, this is puzzle 1, right? Okay, let's consider puzzle 1 for a moment. How would Bob decrypt this? Bob doesn't know the random key. So what Bob does is, Bob loops through, okay, now let's wear Bob's hat, okay? Bob does search for all possible keys until the decryption, right, contains the constant, okay? All right, the constant was sent, of course, in clear text, right? Send the constant ahead of all communication. Alice to Bob sends the constant upfront. This is constant is fixed, it doesn't change. All puzzles have the same constant. Sends the constant to Bob, okay? And then she does this, and then she sends the puzzle, sends n puzzles, right? Not just one, n puzzle, right? Puzzle 1, puzzle 2, and so on. Like, for example, puzzle 2 will be encrypt, another random key 2, right? Another ID 2, and then another key 2, and the same constant, okay? All right, so and so on, n puzzles like this. Bob randomly picks one puzzle. Let's call it puzzle I, okay? Say puzzle I. What he does is he searches for all possible. He does a little for loop and search until he finds the constant after he decrypts it, right? Let's say what he does is basically he calls decrypt function on guessed key, right? For puzzle I, okay. If the decryption output contains, if this contains the constant, then he knows he found the right key. The guess is correct. Guessed key must be the same as the random key that was used to encrypt the ith puzzle. That's all. And then what does Bob do? Bob sends back to Alice the, of course, not the key, the ID or underscore I, which is the puzzle, ith puzzle that he solved, and that has the ID. Okay. It could be a random number again. It's not something easy to guess because the IDs themselves are generated randomly, right? Maybe I should clarify here. How is ID generated? ID was generated by applying an encrypt function on key K1, right? On a number 1, for example, right? So ID I is generated by encrypting the ith element like this, and the key Ki was generated by encrypting the ID. So this is how the IDs and the keys are generated, and he's going to send back the ID to Alice. And now we have, what will Alice do? Alice will just basically recompute the key I by doing an encrypt of ID I she got from Bob. So now, cool. Both Bob and Alice have the same key. That's really nice. Oh, they exchange the same key over the public insecure channel. Okay, let's take a step back and think about why is this secure and what is the work needed for Alice, Bob, and Eve. For Alice, she has to work hard on generating n puzzles, right? So let me analyze the workload. She has to generate. How much work is this needed for Alice? Okay, Alice may have to spend time to generate n puzzles. Okay. If we assume each puzzle takes a constant time because all we are doing is basically generating a random number, calling the encrypt function, maybe we can assume that is a constant time, nothing spectacular there. So order of n complexity for Alice, okay? And then she sends all the n puzzles to Bob. Bob picks one of the puzzles, right? But then he brute force all possible keys, for one puzzle. Okay, which means if we assume it takes 1 unit of time to solve one puzzle for one particular key, then it will take order of n time, about order of c times n to be more precise, to solve one puzzle, right? Solving one puzzle means finding the constant that was sent in clear text. C already I mentioned is a constant. C is a constant as well. Okay. So what about the complexity for Eve now? Eve has a big problem because she doesn't really know how to interpret what is sent back from Bob to Alice. She doesn't know this IDI, right? The only way she would know the random IDI is by decrypting pretty much each and every puzzle. Because remember, the IDI is hidden within the encrypt function, and ID doesn't really map to the puzzle number. Although my description might come across like that, IDs are not mapped to puzzle numbers, right? IDs are random numbers. ID 1 is coming from encrypting the key K1 by number 1. But the puzzle number 1 may have some random number as ID, and the puzzle number 2 has some other random number as ID. So we cannot map ID back to puzzle numbers easily, okay? Just to be clear on that. It's not a continuous number, that's what I'm trying to say. So Eve has to solve all puzzles and brute force each key. That means she has to solve order of C times N times N, right? Which is nothing but order of C times N square. Usually in computer science, we don't care about constants, so we leave the constants out, which is approximately order of N square. Okay, so the amount of work Eve does to break the system is order of N square. What it means is that approximately, if Alice spent 4 hours to generate, say, 4 billion puzzles, I'm just making an example. 4 billion is not a lot, right? It's about 2 power 32, approximately, 2 power 32 puzzles. What will Bob do? Bob will also spend 4 hours approximately to solve one puzzle by brute forcing all possible keys, of course. Okay, so let's spend time on that now. How many attempts Bob has to make to solve a problem? If we are not careful, Bob will not be successful. For example, if I select my C to be 2 power, say 2 power 100, and my N to be 2 power 120, 2 power 28, C times N will be enormous, right? C times N will be as 2 power 128, which is not going to help Bob in solving this problem. So we can't take very, very huge C's. So usually you can imagine something like this, right? Something like this makes sense. Okay, which is 2 power 48, possibly brute forceable in a couple of days on a regular machine. But the homework problem I gave to my students, I had a very simple situation. I only send 65,000 puzzles, right? And in that case, it's not much, right? It's just simple. So all we have to do is, Bob has to do is solve 2 power 26 possible keys. Remember, Bob doesn't solve all the puzzles. Bob only solves one puzzle. So he solves one puzzle by trying all possible 2 power 26 keys, which is not a huge number. It can be done in a few hours, which was the case in my student submission. Okay, and then what will Eve do? Eve has to spend 2 power 26 times 2 power 16, because she has to solve all the 2 power 16 puzzles, which makes her work much, much larger, right? So she has to solve approximately 2 power 52 amount of work, okay, into the constant, of course. So this is a large amount of work for Eve. So this is the idea. And when I submitted this problem to one of my students, he solved it on his machine, and the time it took for him was about so let me show you the context a little bit. So I shared with my student this particular file, right? This file, each line is basically one puzzle, okay? Each line that you're seeing is one puzzle. This is basically what Alice sent to Bob. Bob will pick one of the lines from this particular file, basically one puzzle. He will brute force all possible keys until he finds the constant, okay? As soon as he finds the constant, he knows that he found the right key, and then he sends back the ID. Now Bob and Alice basically know how to arrive at the same key, because the ID is easily mapped to key. On the other side, it's basically calling an encrypt function, taking the key K2 and ID. On the Bob side, of course, that particular ciphertext already has that data. Remember the way I explained the algorithm. Once Bob solves one of the puzzles, he knows the ID, he knows the key. Of course, he doesn't know the random key to try, so he's trying all possible random keys until he finds the constant. So that's basically it. And the effort required for a simplified setting for my students' case is actually something like this. I asked my students to solve, and I gave them one of the, this is the ID, sent back from Bob to Alice, right? Which Eve also knows. So I asked them to play the role of Eve. So they recovered the key K after trying 15 minutes on their laptops. Again, remember my setup is extremely simplified, right? Small number of possible keys, small number of puzzles. But the idea is pretty nice that you could arrive on a common key over an insecure channel by just thinking out of the box, asking Bob to try all possible random keys until he finds the constant. But you make sure that Eve does sort of a polynomial square, right? It's 10 square times polynomial time, while Bob does only linear time work. Of course, in modern days, polynomial time is not good, it's not enough. This particular algorithm that I just talked about is hardly used in practice. Merkle published this idea before Duffy and Hellman published their paper. At least Merkle submitted for publication, but it was rejected for some really weird reasons. And I encourage you to go and read this whole paper. It's really well written paper. Back in 1974, he wrote it. They rejected it, and he explains all the details of the rejection and so on. A little bit of politics as well. He submitted this as part of the graduate work, undergraduate work. His professor didn't understand. He rejected it. And Merkle dropped the course, and he went on to work on this problem, and then he eventually got it published in CACM article, which is one of the established computer science articles. Anyway, as you can see, he added some extra things about Duffy-Hellman and the RSA. After he published, those articles came up, so he has to add those as part of his publication. As you can see, he revised in 1975, but he got it published only in 1977. In the meantime, Duffy-Hellman was published. RSA was also published. Okay. Anyway, that's all. Thank you very much for your attention.